So let's go over a couple exam FM concepts. So first is MACD. So MACD refers to the weighted average time of all the future cash flows. It is always going to be between 0 and n. So it takes the weights are the proportion of the present value of the cash flow out of the sum of all of the total present value. So that's the weight. And then obviously we're multiplying it by the time of each cash flow. So obviously it will always be between 0 and n for a single cash flow because we're only paying at that period of in time. The MACD for that will be the cash flow at that time, the time at that of that cash flow. MACD for an annuity immediate, and these are formulas that it's important for one to understand. So the MACD for an annuity immediate refers to uh, the unit increasing annuity over the present value of that annuity immediate. And then the MACD of a bond sold at par is also that formula of the annuity due of end payments at interest rate I. MACD for cash flow that's increasing geometrically by K, 1 plus I over I minus K. And then as K approaches 0, so if we have a cash flow that, or if we have some perpetuity that is continuously occurring, but it's not increasing, then K would approach to 0 and we would have 1 plus I over I as the MACD. We know that mod D is MACD times V, and it's important to know that MACD will always be greater than mod D. And then another important sort of equation to know is that it's the negative derivative, first derivative of price with respect to I over P of I. So there's going to be some problems where you have to sort of write out the entire price equation with I as the variable, solve for the derivative, and then get mod D. We know that as the price increases, the yield rate or the interest rate will decrease to achieve the same future value. And now these two are the first order modified approximations and the first order Macaulay approximations to get the new price when we have a change in interest rate. So for the first order modified approximation, we have to approximate the new price, we're using mod D. So we do the original price times 1 minus the change in the between the new interest rate and the original interest rate times mod D. And then in first order Macaulay approximation, we're using the original price, we're multiplying that by the multiplicative change between the new interest rate and the older interest rate, and then raising that to the MACD power. We know that passage in time refers to the idea that whenever we're changing a period of time without changing the future cash flows, the Macaulay duration doesn't change. So for example, if you have a Macaulay duration at time period 1, you're moving it to time period 3, and there's no cash flows in between those two time periods. In other words, the present value of the future of the cash flows are the same, then you can simply take the difference of the times and adjust that and then apply that difference to your current MACD. Right? So the future cash flows will remain unchanged from time period T1 to time period T2, and that's why we're able to only adjust for the time and get our new Macaulay duration. For portfolio duration or even portfolio convexity, we apply the same logic, similar logic in the same way we would calculate the Macaulay duration for an asset or a liability, and then we would take the weighted average of each individual asset. And the weights, again, come from the prices, the present value of those prices. So that's where the weights come in, and then we take the duration of each individual asset, and then we weight that by the present value of that asset over the total present value. And then obviously when the coupon rate equals the interest rate, that is when we are considered at par, or in other words, the expected coupon payment equals the actual coupon payment, or FR equals CI, or price equals the redemption amount. If those things hold true, then we know that we're at par. And sometimes you'll hear par value and at par at different times, and you want to make sure that you have a good understanding of the difference between that. Par value means this is the number that you're using to get the coupon payments. At par refers to a type of bond where you know that the price is equal to the redemption amount. And so for bonds with annual coupons at par amount, this is what we can use for the MACD. Convexity holds a similar formula in that we're taking the second derivative with respect to the interest rate, dividing that by the present value with respect to the interest rate, present value of the interest rate. Present value of I, which gets you the present value. And then mod C, we know V squared times mac C plus mac D. Mac D, we went over Macaulay duration, mac C, Macaulay convexity. And a lot of times you're probably not going to directly calculate max C as we noted here above, right? Max C refers to this as well, and mod C refers to this. It's very rare that you're going to actually need to use these to actually do the calculations. It's typically you're going to probably use this formula a lot. You're probably going to use a lot of the derivative operations to calculate mod C. And one of the things that you can remember is that, we know that mod C is the second derivative with respect to I over P of I, and we know that and then we also know that mod D, so both of the mods and mod D is the negative of the first derivative over P of I. So both of the mods you can, and you know that the last the last letter of mod both start with D. You can think of that as a derivative. So whenever you think of mod C, mod D, you can use sort of this way of remembering it, that the D refers to the derivative, and then it equals mod C in this case refers to the second derivative with respect to I over P of I, and mod D refers to the negative of the first derivative with respect to the interest rate over P of I. So that's a way to actually remember that. And then we know portfolio, again, convexity is a similar concept to portfolio duration. You get the convexity of each individual asset, and then you take the weighted average of each asset convexity. Again, the weights come from the present value of the assets, from the proportion of the total present value. So if we have asset A, if we have asset B, asset C, right? Asset A has duration X, B has duration Y, or convexity Y, C has convexity Z. Those would be we would need to take the weighted average of that. How do we get the weighted average of that? We take the present value. What's the present value of A? What's the present value of asset B? What's the present value of asset C? And those would be our weights that we would use in calculating the weighted average of each of the asset convexity. Redington immunization only protects against small interest rates, and full immunization protects against large or any change in interest rates. There's three main concepts you need to know. First, the present value of the asset equals the present value of the liability. So the liability is what you are owing. The asset is what you are investing into to be able to pay out that liability. And then the duration of the asset must equal duration of liability, and then the convexity of the asset must be greater than the convexity of the liability. The first two will give you probably a systems of equations that you will be able to solve to actually get like a duration or a present value or how much of each bond to invest in. So that will give you those specific quantities. Full immunization, as we mentioned, same concepts as the first two, same requirements as the conditions as the first two. The only third one that's different is that at least one asset cash flow has to be before and after each liability cash flow. So the liability, you can think of that has to be a sandwich or like the middle of a sandwich between the two assets. So here we have a liability at this time period, this time step, we have an asset before and we have an asset after. So this would satisfy the conditions for full immunization. And one of the ways that you can test if actually Redington immunization is achieved is if it meets full immunization, that automatically implies that Redington immunization is already achieved. And it's much easier to detect if full immunization is achieved because you only have to see if there is one asset cash flow before and after the liability cash flow. If that is the case, then you already know that Redington immunization is then achieved as well. And then finally, we have exact matching. So this is where the only assumption for exact matching is that the cash flows are fixed. And this is where the amount, the exact amount and timing of the liability cash flows match exactly. And so you would start off with sort of creating this diagram where you would go with the longest asset, and then you match that, uh, appropriately allocate the coupons, try to match then the second shortest asset, and so on until you get at every single time step the amount that of the liability matches. And so that's exact matching. For Macaulay iteration of bonds, which is a typical problem that comes up, we can see and we can derive this formula for the Macaulay iteration of a bond, which is FR times the unit increasing annuity plus CNVN over the present value of the bond. And we can use for the unit increasing annuity, we can use our TVM keys formula for increasing annuity for n years to actually get that amount. And then another concept is if you ever encounter an equation with more than two v's, so if you have like v squared or v, you could use the cash flow keys, but you should remember to only use them if you are certain that there will only be one viable solution. If you know that there are multiple viable solutions, then it's advised to then just use the quadratic formula because you won't be able to get like the two different solutions. And if the question requires you to actually know the two different solutions, maybe it's like what's the absolute difference between the two possible interest rates that could result from this, then you would need to use the quadratic formula to actually get that instead of just using the TVM keys, which will only get you one solution. And then let's go to the concept of loans again. So obviously this is another important topic. One version of these types of problems is when the payment amount is level, meaning we have the same payment amount for every single time step. So we start off with the original loan amount. Note that the interest due will always be equal to the interest rate times the previous outstanding balance. So for the first one, the amount of interest due would always equal the interest rate times the outstanding balance, and so on. One of the things to note, one of the main concepts, if it's level payment or if it's non-level payment, is that the payment amount will always be broken up into the interest due and the principal repaid. So if you take the sum of the interest due and the principal repaid, you will always get the payment amount, no matter if the payment amount is level or if it varies. You will always get the sum of the interest due and principal repaid to be equal to the payment. So that's one of, and then the other thing that always will hold true, no matter if you have level payments or you have non-level payments, is that the interest due will always equal to the interest rate times the previous outstanding balance. So that is another thing, regardless of if it's level or non-level, that will always hold true. Another thing that will always hold true is to get from one outstanding balance to the next outstanding balance. So to get from OB1, outstanding balance at time period 1, to OB2, you subtract the principal repaid at that time step. So OB2 will equal OB1 minus principal repaid at time period 1. Another way to go about doing this is you accumulate the outstanding balance with the appropriate interest, and then you subtract the payment. So this is what we call the retrospective method, is where we take the original loan amount, accumulate it by interest by T years, right? T, whatever the time period that you're looking at, subtract it by the accumulated amount of the payments that you have made, and that will get you to your outstanding balance. Outstanding balance is also viewed as the present value of the future cash flows. So that's another important thing to note. If we take the sum of all of the interest dues, if we take the sum of all of the principal paid, that will get us to the sum of all of the payments. And it's important to note that the sum of the principal repaid will equal the loan amount, which is really what, if you think about, right, principal repaid, we're repaying the original loan amount without any interest. So that's an important thing to know as well. There will be questions, or there could be questions, where you get some relationship between the payment and the interest due. So, for example, one of the questions could be that, hey, the payment is actually exactly the same as the interest due, and in that case, our principal repaid is zero. And another type of question could be that, hey, the payment is actually 50% higher or 150% of the interest due. In that case, interest due is X, payment is 1.5X, and then principal paid is half of the interest due. And with that, you can create a relationship uh, between the outstanding balances. And so in that scenario, and typically in those types of questions where you have some relationship between the payment and interest due, it's typically the case that you can make some sort of relationship between consecutive outstanding balances. And you can use that to get an outstanding balance at time period 10 or time period 9 or time period whatever time period you need. So that's one of the sort of the nuances of that question. We went over the constant conditions for both level and non-level payments. And now if we look at annuities, and again, you have to do practice problems to really understand these. One thing I do want to emphasize is for balloon or drop payments, when we do get the outstanding balance by calculating the future value, you must remember that that is the value at that period. So to get to the drop amount or even the balloon amount, you have to accumulate that amount that you get from the future value by the interest rate. So what we're saying is that if you're at time period 1, you get the outstanding balance at time period 4, and then you have some balloon amount or drop payment at time period 5, you get some amount at time period 4. That's not what you're going to be paying at time period 5, right? You have to accumulate that interest to get the amount that you're going to be paying for the balloon or drop at time period 5, right? So you have to there will be choices where it will just be the amount of time period 4, and many students would fall for that trick, but you have to understand that you have to accumulate for the interest to get to that balloon or drop payment. And then we have continuous annuities, which you must sort of internalize and memorize this formula as well. And then we have formula for geometric progression. This comes up a lot. And then if it's a geometric progression with payments with n equal to infinity, or if it continuously goes on, then you can do 1 over I minus k and then multiply it by the payment. And then we have these different formulas here. Our arithmetic progression for infinity, p over I plus q over I squared. This is for perpetuity immediate. And then we have similar concept for continuously increasing annuities. One of the additional things we want to emphasize is there could be some questions where there's a repeating reverse. So repeating reverse refers to the fact that you have a unit increasing annuity, so from time period 1 to time period 4, and then a unit decreasing annuity from that period on. So it would be 1, 2, 3, 4, and then immediately after the 4, you have a 3, 2, 1. Like you can solve this through obviously many different ways, right? One way is to create an annuity immediate with the 1, 2, 3, 4, and then you can create or a unit increasing annuity immediate with the 1, 2, 3, 4, and then you can start from the 3, 2, 1, get the present value of that at time period 4, right? That would be a unit decreasing annuity immediate, get the present value of that at time period 4, and then discount it 4 years so you can get the present value at time 0. But another way to do this, remember this one shortcut, is at the first payment date. If you have this repeating reverse pattern, then you can use the annuity due at time period 4 at I and square that to get the present value at the first payment.